My name is Sha Hsing. I am Program Manager for Data Analytics and Infrastructure in Dr. Inga Lennis's division, specifically part of the Ambulatory Management team. I'll be discussing quantitative data usage from a data and reporting resources and methods perspective. Now, I've looked at the course description and also each of your introductory bios. We have a very diverse classroom and a short time together to cover a broad range. So here's how I'm going to approach it. First of all, some people want quant methods and data, vocabulary and data methodologies. Some people are looking to transform medical practice at a very senior management level. Some are looking to transform healthcare policy and architecture. Some people are here just for background and career advancement within their current jobs. So I'm going to touch on a wide gamut of topics. But to fit, I'm going to try not to repeat things that you can read about, but rather focus on key takeaways, tips, and tricks. I'm going to share some of my own advice, my own professional experience and points of view. And also in some cases, I'm going to dump and run. That is, quickly dump a list of ideas that I think might be useful to a particularly small segment of the class and take advantage of the streaming format where you can pause and go back and decompress material if it's of interest to you. In particular, we did get feedback last year, and I saw this year's intros, desire for more emphasis on statistics. And this is not a statistics course, but I will have my first section be a kind of a tour of statistics focused on key takeaways and maybe some insights that might be useful for advanced practitioners. But I hope that even people who are not very familiar with statistics will get at least a foundational view of some of the key concepts that I think are useful for somebody doing clinical operations management. Second, we'll talk about how to organize people. We'll look at some, just a few data, analytic, and reporting products. And we'll look at how to organize data, and I'll touch upon CRM, why we are using Salesforce customer relationship management as a platform. And then finally, we'll use some time left to walk through some real world cases to illustrate some of the key takeaways. Here we go. So we'll start with a quick run through of some basic statistical concepts, focusing on a few key practical takeaways. So statistics is just a formal mathematical way to answer everyday quantitative questions in a consistent, provable way. These questions, there's a hierarchy of questions. The first question is, where is it? And that's called the location statistic, such as the mean. Second, how spread out is it? That's the dispersion statistic, such as variance and standard deviation. Third, how symmetric is the spread? Fourth, how lumpy, and so on and so on. But in every case, for every answer, we also ask, how sure are we? Okay. So we're asking in this slide, the first question is, where is it? That's the location statistic, and it's an average of some kind. If you are not familiar with the differences between mean, median, and mode, Google it. The differences are highly important. We're going to focus today on mean because almost all the studies and measures you see are means or based on means. Even if they are means of medians or means of modes or something. For example, if you talk about the growth rate in the median case fatality, well, what you're actually talking about is the average, a mean of changes in median growth across a series of time periods. So means are fundamental. And the way we're going to measure this pizza and describe this pizza is by scattering anchovy eyeballs. All right. So these blue dots represent sampling points. I'm going to drop these eyeballs over and measure each one's location as a distance from the origin. To get the mean, well, mean is sum divided by the count. So I'm going to add the distances and divide by the count to get the mean distances. Now, first, on the vertical axis, Let's say that the bottom of the pizza has an anchovy eye here that's 1 inch up, and the highest one is about 11 inches up. And if the eyes are evenly spread out, the average distance of the eyes is about 6 inches up from the origin. Okay? So the center of the pizza is 6 inches high. On the x-axis, let's say that the eyeball distances vary from 4 to 14 inches. Then if you do the math, the center is 9 inches to the right. And therefore, we can say that the center of the pizza is located at 9, 6, and that it's 9 inches to the right and 6 inches up. Location is the mean, which is the sum divided by the count. Now, the more interesting question is the next question, which is, how spread out is it? Dispersion. Now, we could add up all these distances and say, oh, that's how spread out it is. Just add up the distance of each anchovy eye from the center. You could also take the average. But it doesn't matter. Either way you do it, we'd run into a problem. If you double the distances, would the pizza be twice as spread out? So let's ask this question. Let's say the pizza, well, we did figure out this is a 10-inch pizza. Let's say it's 1 centimeter thick. And we want to spread it out twice as much. What does that mean? We want a pizza that's half a centimeter thick. How big would the pizza have to be? We're starting with a 10-inch pizza. How big does it have to be? Well, if you do the math, it's about 14.12, 14214 inches. The distances are 1.414214 times the original distances. What's special about 1.414214? So it's the square root of 2. Now, to get some insight into why, ask this question. What if you doubled the size of the pizza from 10 inches to 20 inches? How much thinner would it be? We're starting with a fixed volume of dough. Volume is pi r squared times the height, the thickness of the pizza. If you double the radius of the pizza, multiply by 2, the radius squared goes up by 4, so the thickness has to go down to 1/4. So the answer is you double the distance, you quadruple the spread. So how spread out a phenomenon is a function of the square of the distances of observations of that phenomenon from the mean. That's why variances, standard deviations, chi-squares, they're all functions of the sum of squared deviations from the center. The significance of this is that outliers have a disproportionate impact on measures of spread. This anchovy eyeball has a lot more impact on what you're going to conclude from your study than this one. In fact, once you go beyond means, means are just sums divided by counts. It's a very linear thing. But pretty much every other statistic is disproportionately influenced by observational distances from the mean. Outliers have an outsized impact on our statistics. And one common application of that is that confidence intervals are a function of effect size and dispersion, your measure of spreadoutiness. Well, there are two things we know, right? First of all, we know that this increases disproportionately fast as you look at outliers. Outliers have a disproportionate impact on dispersion. And secondly, when you divide one number by another number, the denominator, the number on the bottom, has a huge impact on the quotient. So confidence is hugely influenced by outliers. Now, this effect influences how we understand many, 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 many things. So regression analysis, including, like if you're doing Excel trend lines, it doesn't matter whether you take linear or whatever, it's still going to be influenced by outliers. It's still going to be minimizing sums of squares and so forth. Cluster analysis in identifying odds ratios, making forecasts, error bands. These are all the stock and trade of healthcare literature. And they're used to determine drivers. They're used to make attributions, what's causing what. They're used to segment patient populations and also used to forecast, to estimate resource needs and costs. I'm going to wrap up this section on basic stats with key takeaways about sample size, because that is also highly nonlinear and related to confidence and something to deal with a lot in your literature. So in readings, you can look up sample size metrics and formulas. How big does a sample need to be to yield a certain level of confidence? Well, confidence is highly nonlinear. In particular, I'd like to throw out a few highlights. First, once you get a few thousand, the increases in sample size don't add much confidence. However, you do need larger sample sizes in many cases. First, if you want to slice and dice and look at subsets of your sample, you need to increase your sample size to make sure that each of your slices has a couple thousand or whatever you need to get that confidence interval you're interested in. So try to anticipate that ahead of time, because I always try to do at least 3 times the sample size my calculator tells me I need, because usually you end up needing to slice and dice in ways you didn't anticipate originally. Also, you need to allow for plenty of room for contamination of your sample. There may be many observations you have to throw out for one reason or another. Larger samples are also needed to reserve validation samples. That is, you need part of the sample to train the model, to fit the model, and then you want to have another part of the model to test it against. Another point is that if you see sample sizes below 30-ish, small sample sizes, they better be using special techniques to adjust for that, because the standard statistical rules fail, and you need to make adjustments because of that. It's interesting, it's a common myth that if you're sampling a larger population, let's say you're taking a poll of the whole United States, you need more respondents than if you're sampling a small population. Let's say you're taking a poll of just your city. It's not really true. Population size matters, but only up to a point, and then becomes a very small factor. Confidence depends more on sample size than population size for large populations. So for example, about 1,400 respondents is all you need for a 3% margin of error. That's true whether you're trying to forecast election results for a city or for the US. Now, it's also very important to remember every single time you see these confidence intervals and margins of error is that they reflect only sample error. Sampling error is the probability that if you take a random sample twice, you'll get 2 different sets of people. Sampling error is only one source of error. There are many, many other sources of error, and the most common source of error that I run across is, are you sampling the right thing? Okay. All right. This section about how to irritate a statistician is really just key questions you should ask yourself, or if you want to irritate a statistician, you can ask him or her when you see results that are provided. When it comes to the data, outliers, we've already covered why that's important. How and why did you decide how to handle the outliers? Did you exclude them, include them? Did you have a threshold? You have to prove why you did it, and you also have to be able to show how the results would differ if you changed how you handled the outliers. If you have a threshold for throwing out outliers, why did you pick that? And how sensitive are your results to that assumption? The assumption of normality, a lot of these metrics depend on normality. Or, okay, so you can ask, well, is this normally distributed? And they say, okay, well, actually, I assumed a different distribution It doesn't matter what distribution is assumed. The statistician is going to be using some off-the-shelf distribution. And you can test whether the actual distribution of the phenomenon you're describing matches that off-the-shelf distribution. And it's not hard to do so, but it needs to be done. The next question is, are the events independent? And it's irritating because they rarely are. So for example, by independence, that means that when you see one event, whether let's say whether one person lived or died, has no effect on whether another person lived or died. Well, 2008 financial crisis, correlated risk was a big, big, big oversight. The probability of 2 loans failing is not just the probability of 1 loan failing times the probability of another loan failing, the way you would do coin flips. No, when you have, it could be one thing causing both loans to fail. So if one loan fails, of course the second loan is going to fail because they both depend on the same thing, housing values, let's say. Also, when one loan fails, that can weaken the financial strength of other debt assets and cascade. In healthcare, you might have, you're talking about what's the probability of somebody will get sick. Well, in a family, if there's an illness of a caregiver, that might increase the probability of illness in other family members in the same household, right? So correlated. In that case, these events are not independent. And that can have a huge impact on both your confidence and your measured impact, effect sizes. Do your training and validation data match the population that you're going to apply your learnings to? Well, very, very often studies are done in volunteers. Volunteers are a biased sample of the population. Studies often exclude pregnant women and children. Very importantly, studies often exclude people with certain prior pre-existing conditions or already being treated for other things. And in the real world, you are going to be applying learnings in a world that's very diverse, and also you're going to care a lot about interactions. And if you have a purified data set to sample from, you won't be able to see those interactions. Does your training do time series analysis? Time series analysis, first of all, there's an overlap between that and training data matching the actual data you're going to apply it to. Things change over time. So if you are looking at historical data and you say, hey, I brought 20 years of data, that could be a bad thing because you're applying it to the future, and things 20 years ago were very, very different from the future. We call that regime change. In other words, when you collected the data, was there a different culture? Were there regulatory changes? Were there changes in population preferences? All those things could make that study irrelevant to the future period you're going to apply results to. Another statistical problem with time series analysis is stationarity. Fancy word, just say it, and it makes statisticians go crazy, unless you did it right. But basically, stationarity, is your data stationary? Is asking, is there a trend in your data, and did you take the trend out? Because trends exaggerate correlations and destroy confidence metrics. Basically, everything grows over time. Everything tends to get better. And so whatever you introduce at a point in time will seem to be correlated with improved outcomes because things are getting better. Okay, I'm going to skip the example. No, let me talk quickly. Example, Prevent History program was a program to improve dental outcomes through a series of educational interventions and procedural changes. And it was correlated with great improvements in outcome. I did the analysis and said, okay, yeah, you had great improvements in outcome, but the whole state had great improvements in outcome. Everybody was changing. It wasn't the program that drove the change. Questions about design? Did you adjust for confounding factors? I'm going to short circuit that a little bit, but basically, there are a lot of confounding factors that people tend to choose from the usual suspects, like age, gender, initial clinical scores, but they seldom use statistical techniques to figure out what confounding factors are appropriate. Decision trees, determinant analysis, there are statistical ways to figure out what you should use. And if you leave out confounding factors, that pretty much invalidates a lot of your measures. Attitudes, behavior are often underrepresented, and they kill confidence levels and can cause bias. Similarly, are driver X and Y correlated? Most statistical techniques get thrown off if the drivers are correlated. Income and race, for example, they're not two separate things. They're correlated. They overlap a lot. Diabetes and heart disease. Correlation, multicollinearity is called, can cause massive instability in your model. And you can mitigate this, as a side note, by adding into your model just residuals of variables after they're regressed against the existing models. Technical note. What statistical method did you use to select confounding factors? That's going back to the first. You can use, okay. I think I mentioned determinant analysis, decision trees, and so forth, right? And let's see, what's a double blind? Well, fortunately, a lot of the clinical trials are double-blinded. Very, very important because observation effects are strong and proven. And we'll see that in the last section on real-world examples. There's a famous study of knee surgery found that knee surgeries were not effective in that particular type of knee surgery. That was a single blind thing. The patient didn't know whether they got the real one or the fake one. It's very hard to make a double blind. The doctor knew, of course, but still, it's good enough for that. But when it came to, for example, a lot of the COVID studies, there was just a huge amount of studies that were unforgivably defective, in my opinion. Published studies where it wasn't blinded, sampling was bad, and so forth. Did you validate out of sample? This is an irritating question because often it's impossible to do it because the sample size is not big enough, but it's really important. So traditionally what you do is you take a data set, you hold out a portion and train the model on that, and then you prove out the model on the part you held out. But there should be no big surprise that the model is going to validate well against the holdout sample, because the training and holdout data sets were randomly selected from the same population. So they should be very similar, and therefore the models should work for both. But so you really want to validate against a different kind of population. For example, one trainer on one period of time validated on another trainer on west of the Mississippi, validate against east of the Mississippi. It's difficult. Multiple selection error, very, very common problem. Basically, it means taking several shots at the same target. So regression fishing is an example. Some meta-analysis boils down to multiple selection, taking multiple shots at the same target. Also, you might see a study with multiple endpoints, but using the same trial population. If you are taking more than one shot at the same target, of course, you're going to have a very much higher probability that one of your shots is going to be statistically significant. There's almost no, there are many ways to adjust for it. Almost none of them are adequate. Correlated drivers are another example of taking multiple shots at the same target. So for example, if you have a study where your drivers include family size, income, and education, you're basically measuring economic class 3 different ways. You know, they're not exactly the same, but there's a lot of overlap. All right, so quickly run through some techniques, advances, and show how, well, the point I want to make is that they all have buried in them statistical weaknesses like the ones we covered. Now, the methods are sometimes paired with other techniques to try to mitigate these weaknesses, statistical weaknesses, but with varying success. And some of these mitigation factors often hide the weaknesses. Data mining, in my shorthand, data mining is statistics for computer scientists who don't like math. It still applies statistical methods, but it does so to dirtier data and with assumptions loosened. Then it uses massive validation, which is really just trial and error, to compensate. It's used particularly for pattern detection and classification. Okay, neural networks came next. This is kind of like in historical time order. Neural network is just regression with fancy mathematical twist. So same, it's a statistical technique with the same statistical pitfalls, plus some other ones. Genetic algorithms apply statistical methods, but it automates the trial and error process with some sensible rules. Machine learning applies statistical methods, but it automates the trial and error process with less sensible rules and therefore can do it much faster. So it does a lot more trial and error, and then it does even more validation to throw out the bad models. So what it thinks are the bad models. So there are two parts to model fitting. One is you find the pattern. Second part is to validate or score how well the pattern actually fits the data. A lot of machine learning, AI techniques, et cetera, are using non-statistical methods to do the scoring part, but still relying on statistical methods for the model fitting part. Not always, but that's quite often. So machine learning or genetic algorithms or AI, they're going to apply rules to score the model and to weed out the bad ones. They're using rules that try to mitigate statistical traps and weaknesses. But the validation part brings up problems of its own. For example, compensating for outlier influence in scoring model performance can lead to reinforcing prejudices and historical norms. The influence of squared deviations, if you throw out outliers because you're worried about outliers influencing your results, well, you have to remember that the reason outliers have a disproportionate impact is rooted on some experiential realities. Like the pizza example, that was just based on math and physics, right? And another example in terms of how humans deal with risk. If you're backing a car out of your driveway 99 times and the 100th time you back over the family cat, you know, Liberty Mutual's machine learning algorithm might say, okay, fine, give you a pass. But your kid's assessment of your driving ability has just taken a nosedive. All right, we'll take a little break here and do a little knowledge check, and then we'll continue. All right, next section, let's get down to brass tacks. How I think about building a team, some thoughts that I have about data architectures at a high level, some examples of useful common products and what I look for in them. I'll dig into that a little more in the cases example at the end, applications section, and a quick note on the emerging role of CRM in healthcare. There are three models that I'll talk about for deploying analytics in a multi-unit complex organization. The Center of Excellence model was developed several decades back, and it takes advantage of the fact that analysts work best when they're working together. You get synergy and cross-training. They have cross-functional contextual awareness when they're all working in the same, working together. And because they're working on a variety of things, learning from each other, you get better staff retention and it's easier to hire. And because you can more easily swap off people from one project to another, you can achieve better resource capacity utilization. Because you're sharing best practices and data sets and so forth, you have more standardization and therefore numbers that box that are consistent. Also because these people are separated from the business units that are consuming the analytics, there's some neutrality of viewpoint and a neutral viewpoint toward prioritization of projects also. And of course, there are often scale efficiencies when you have more people working in a concentrated center of excellence. Now, the current state MS General Brigham is a little bit like, it's almost like the opposite of the Center of Excellence. It's a distributed, it looks more like a distributed model. And in a distributed model, you have analysts wherever they're needed. It's good when a lot of the knowledge is local and not well documented. This also reduces the path between the distance between people who are using analysis from the people who are generating it, and that's good. It also lets people who are managing these business units have a very predictable pool of very stable geniuses they can rely on. Right? It's not going to be taken away from them. Plus, competition can actually, co-opetition can actually drive unit productivity up. It can actually help reduce costs. I'll talk about that a little bit more later about how if you aggregate everybody, that can lead to very expensive innovations. Not innovations, expensive project proposals. Now, distributed, I think the distributed model has proven out also to be the best way to drive innovation, though you might hit some barriers in the dissemination of innovation. Okay, I think what is the best compromise is in a hub and spoke model, you can get scale efficiencies and therefore reduce the size of each team, but you're still doing distributed. And the way you get the scale efficiencies is by having the hub support the distributed teams and do complementary work. Okay. For a large organization, I think the Center of Excellence model has proven tricky. It's still good in many cases, but in terms of insights and innovations, it can be a little bit stifling. And even in terms of cost effectiveness, the amassed power tends to generate ambitious, expensive infrastructure projects and internal monopolies. There may be some barriers to responsiveness due to turf issues. These can be solved through management, but they're often not executed well. So I do like the hub and spoke model, or for a smaller organization, it could even be one team with a tiered continuum from first responders to a production tier, even if it's 1 or 2 people per tier. Okay, how do you organize data? Some vocabulary. I'm putting up 4 data design paradigms, but what I'm really going to get at is my point of view on big data. But these ways of organizing data vary along 2 dimensions. One is the quantity of data. And the second is how structured the data is. What makes big data is not size, but structuredness. Specifically, the fact that big data is less structured. Now, big data technology also not only stores large amounts of data, but spreads the data in a distributed way with distributed processing and even some distributed analytics. So it's really qualitatively different. Big data tech did become necessary when data sets got large. But the key attribute is not what you read in the literature about the 3 or the 4 or the 7 V's, like different authors use different numbers of V's, but they stand for velocity, variability, veracity, things like that. The key attribute is that big data tech uniquely handles unstructured data well. So what does that mean? Well, first of all, what's structured data? To structure data, you classify, simplify, and put data in boxes so that you or your applications can find them easily. Structured data saves read-write time, it saves processor time, and therefore addresses speed barriers, especially speed barriers with older technology. But the hierarchy and the boxes are predetermined. if you have a new hierarchy or you need new boxes, you need to go through a design, build, deploy process. You need to go through change management, and that costs time and labor. The right structure depends on the user and the use. So you may also have to replicate the data with different data models for different users. Now, unstructured data, I think of as what the senses pick up from the physical world, like images, like sounds, and yes, also free text numbers. But the idea is that, so here's an example. Here's a sound wave. How do you model a voice recording? Well, if you were using structured data sets, you can model it based on meaning. What's the subject matter of this voice, this phrase? Let's say, what's the sentiment? What are the conclusions and questions? How reliable is it? Right? You could also model it based on the physical attributes. What's the signal to noise ratio? What's the amplitude? What's the duration? What's the pitch range? Or you could model it based on source, right? Who's speaking, when, time and date. What's the location, right? But once you pick how you model it, and if you want to look at it from a different point of view, you need a different data model. Unstructured data says, just put the sound wave in an unstructured data set and leave it there. Figure out how to describe it when you actually use it. Okay. Now, unstructured also means not model on read instead of model on write. See, your applications are generally going to need some structure, but in an unstructured model, you apply the modeling, the structure to the data when you pull it out and use it right before you give it to the application that needs the data. So we call that model on read. Model on write is the old-fashioned method where as soon as you get the raw data, before you put it into storage, you apply a model to it. That's model on write. Okay. Now, an increasing share of the data that you're working with is often not even in your domain. For example, sensory data from patients or households, or Fitbits even, and Apple Watches and so forth. There's non-clinical behavioral, environmental, and attitudinal data, often third party, that might be outside of your universe. Big data also has the advantage of generally being lower total cost of ownership, but there could be a high upfront investment if you're transitioning, and you also have to be careful to know where you're going to hire people from to build and maintain it. That particular set of skill sets is very different from the traditional skill sets. Big data platforms are scalable and scalable with high reliability, and they are very fast. But very importantly, they also don't care too much about who or who's using the data or how it's used. So it's more agnostic and more flexible that way. I won't get into the question, but this is an important question of on-site, off-site, or whether you do it on-site cloud. And it's particularly important for big data because of the complex hardware structure behind it. All right, let's, before our next break, let's take a quick look at just a few products that a typical team using a typical set of data might produce. Here's an example of our architecture, our schema for our dashboard in ambulatory management, AM Dashboard 360. The gray boxes are a layer of the dashboard which, for an executive audience to provide situational awareness. The idea here is to put together measures of access is how patients get to an encounter. Resources are how we make that encounter happen. And then co-located with these measures, we also show what we can about patient outcomes, the so what question. The second layer allows managers to drill down to detect problems and avoid problems, and to determine what's driving emerging or potential problems. And then the teal layer on the bottom, we have targeted analytics for tracking interventions. And they're characterized, they're different from these other types of dashboard reports because these have goals and evaluations. They measure progress toward the goals, and they identify next steps, or they at least point you toward what the right next step is. So I'm going to skip some of the graphical part, just walk through 3 guiding principles. 1, measure what matters. Don't measure everything. Secondly, reports and dashboards should be seen, not read. You should be able to look at it and get the idea of how it's organized, and also get a very quick idea about what the key takeaway is. Now, that doesn't preclude having additional reading content as long as it doesn't obscure the key takeaways. And it doesn't mean everything has to be a picture. Numbers and text can also be seen and quickly interpreted. Key takeaway section is an example of a very important element, I think, of a report. That's text, but easy to see, and you don't have to digest a whole lot of words or numbers. And then what's different about this picture down here is that it tells you so what. Everything should answer a so what question. If it doesn't answer a so what question, it doesn't really need to be there. In reality, there may be clients who are saying, hey, I want this on it, and you might have to throw it on it, but try to resist that. Here's an example of that 3rd tier reporting, the bottom of that chart of the schema that I shared. This is a tracking report for an intervention. And sorry for the fuzziness, I JPEG'd it to blind as much as I could. The top charts show volume on the left and efficiency on the right. So this is a general idea, a general concept to bring to measuring almost everything, which is how much and how efficient. Second layer, and it shows the trend, so you can see. And then the second layer is at a glance, where you were last period, where you are in this period, and what is your benchmark, what is your goal. The difference between last period and this period is particularly important because this is a periodic report, and each period's report should generate recommendations about what to do. And then you should see the effect of what you did in the next report. And then the final section at the bottom here shows progress toward goal, shows percent of days left, and in this case, it's tracking also resources expended because there was a budget for it, so percent of dollars spent. And like I said, there should always be a key takeaway section that says, what do you do next, and what do I expect to happen? To do a scorecard. This is actually the lower right-hand corner of a glossy bifold. The rest of it was text that introduces and explains. Another important part of this, of a scorecard in general, is that it's personally presented by a doctor with the manager. Sometimes you might have to send it electronically or mail or something, but mediation is useful. And the key attributes of a good scorecard, I'll talk more about in the cases section, but it's worth repeating. The metrics should be collaborative, they should be relevant, they should be clear, timely, achievable benchmarks, perceived as fair, and be efficient to produce. All right. Last for this section, CRM. We have implemented a customer relationship management platform in ambulatory management. In particular, we're using Salesforce. The purpose of CRM is to in general, CRM is to optimize behavior through managed integrated communication of the right content at the right time, to the right target, to the right channel. And that sounds awfully like what ambulatory management boils down to, because we're not actually giving medicines or anything, but we're communicating to people, or communicating a wide range of things. It could be everything from rules to information to training and so forth, but we're communicating in order to influence behavior. And we can communicate in many ways. We have a very complex set of resources and people and projects and so forth, so you need to keep track of all of that. CRM is well designed to do that. CRM solutions came about historically because people got tired of working with IT, and they wanted a way to do things. They wanted a data repository. They wanted ways to report. They want to do stuff without having to go through a lot of IT and DevOps, which is very slow, usually unpredictable, often didn't result in what you needed, and almost always expensive. So what this does is the CRM allows you to integrate information with action. And it also, CRM is a proven behavior changer. And it changes behavior through contact management, content management, and targeting and scoring. Now, what we have hung onto this infrastructure of Salesforce is a survey. Gizmo is a survey tool where we're using it for data capture. We have Constant Contact for communications generation and for contact management and risk management. And we have Cloud Coach for project and resource management and for workflow management. And the idea is to have it all within one interface. Let's skip this one. So let's just take a quick knowledge check, and then we'll continue in a minute. All right, final section, we're going to look at some real-world examples, and with a particular eye toward what to do and what not to do. Here's an example of a study that BJ's did, the store chain, to illustrate the error of confusing process with outcome. Now, there is much better awareness these days of how important it is to measure outcome rather than just process. But there's still, I think, opportunity to a need to think deeply about and validate what the right outcome is. So this study was about wellness programs. Very popular, very big, very expensive. And BJ studied wellness programs and a random sample basis, a very large scale. And the wellness program involved handing out Fitbits and had some training material too. And clearly handing out Fitbits is not success. It's clearly process. But they did find that people exercised more in the treatment group, the stores that had the wellness program. But is that outcome? Not really. Outcome from the corporate standpoint and from a wellness standpoint was better health outcomes at lower cost. And when they looked at that, they did not see any benefits in terms of health outcomes or cost. So wellness programs in this study. I'm not saying you should abandon wellness programs, but I'm saying they did this the right way. They looked at the right outcome. All right, DARE. National, very famous program. You still see cars with DARE stickers on their bumpers. And this was a program for drug prevention. It ended up costing about $200 per student to execute the program. And in many cases, drug usage declined in schools where the program was implemented. But it was because the program was targeted at the highest drug use areas. And regression to the mean drove many false successes or false success stories among crime and poverty programs in the 1960s. precisely because they were targeted based on extremes of need. And on average, extremes move toward the average. Also, this program suffered from lack of controls. If you had a control group, you would have seen that both your control group and your treatment group were improving due to regression to the mean. And it suffered from observation effects, which is if you study anybody, they tend to perform better because they're being studied. And it suffered from affirmation bias, which is if you're expecting a good outcome, even if you think you're using rigorous techniques, historically, empirically, it's easy to prove. You tend to come up with studies that confirm your prior expectations. In fact, when they did, it's not popular anymore. In fact, because people did start doing in the 70s, more in the 80s, and then as a rule in the 90s onward, outcome measurement. In some cases, they actually found that drug usage increased. They think it was because the program was putting drug usage on a pedestal for anti-establishmentarianist people, like youngsters. All right, observation effect. I mentioned that in passing. Here's an example. Here's a study where the intervention group was treated, of course, but they took the control group, they split it into two control groups. One part of the control group, which was not treated, knew they were being studied, and the other part did not know they were being studied. So fine, the treatment group did have better outcomes. But the group that was not treated but knew they were being studied also had better outcomes than the group that was not treated but didn't know they were being studied. This is the observation effect. Okay, I saw that in a previous job where we had a program, a STAR, health quality STAR program. And when I looked at the time series, the effect became, the positive impact began upon announcement of the program, not upon the actual launch of the changes in behavior. And the effect declined back toward the baseline, even though the level of intervention, the number of doctors enrolled and the amount of communications and actual bonuses paid too, even though the interventions increased over time. So you put all that together, what drove the improvement? Probably the announcement effect or the observation effect, the fact that they were so excited about this new program. Mayo Clinic here, let's see, X factor. X factor is when A looks like it causes B because A and B move together, but it turns out that A and B are both being driven by X. And economists use the example of umbrellas. People who leave, if you see people leaving the house with umbrellas, there's a high probability it's going to rain. It's not the umbrellas that caused the rain, it's the forecast. Well, it didn't cause the rain, but the pre-existing conditions of atmospheric conditions that were likely to cause rain caused both the umbrella carrying and eventually the rain. And this is a cancer study where people found that on average, patients treated with this drug performed better. But they were finding that Gleevec was failing also in a remarkable number of cases. And it turns out it's because they thought that Gleevec was working by targeting one target, one protein, but that wasn't it. It was actually targeting a different protein. So that X factor, they had the wrong X factor, and that meant that a lot of patients were getting the drug who could not benefit from that drug. Let's see an example. Okay. You'll get these slides, so you can read some more of these. But here's I didn't put a graphic on this, but post hoc fallacy is just saying that Just because something follows something else doesn't mean that the first thing caused the second thing. Obvious when you put it that way, but the post hoc fallacy still happens a lot. We had a program where we paid an incentive for increasing preventive care. And we wanted to see, and we did see that preventive procedures increased. And let's see, do I have it here? No. But when we looked at when actually, well, first of all, the preventive procedures increased both among people who were paid and people who weren't paid. And they tended to increase before they were even aware of the program. I'm going to skip this. This is about targeting. But the key takeaway here is if you're trying to drive change, you might not want to target the people who are the worst performing, because resistors, the people who are worst performing, are often, well, first of all, they may be performing at a low level for a good reason, such as the measure you're measuring them against isn't applicable to them, or they have a special population that's particularly resistant or whatever. Right? But in general, your best target for driving change may be somebody near the top rather than the very, very bottom. Okay? To determine that, you need to look at incremental impacts. And again, I'm going to leave that for later reading. But if you work your way through the table, you'll be able to find for each of these groups how much they changed due to the treatment, and also how much they changed per expenditure of resource. So your target actually should be where you get the most bang for your buck. And that's often not the bottom. This is a huge source of error. Being a slave to p-values. P-value tells you type 1 error, which is the probability that which is the probability that you might be finding something that isn't true. But when it comes to public health, it's often important to do something rather than nothing. And what you don't want to do is you don't want to miss something that might be true. Type 2 error in many applications, especially outside of the point of care. The point of care, do no harm. You don't want to do something that you don't know is going to be the right thing to do. But in many other applications, if you don't do something, things are going to go bad. So type 2 error in that case may be more important. P-value does not tell you that. P-value is also only a function of sample error. And as I mentioned, there are many, many other sources of error, and they overwhelm sampling error often. Another reason p-value is often misleading is multiple testing happens a lot. And multiple testing error is when you take several shots at finding success. If you're looking for 95% confidence and you take 5,000 shots at success, yes, 5% of those on average are going to come out positive. You're going to find something. So if you test a whole series of drugs for success, or if you take one drug and look at multiple endpoints, you have to adjust the p-value by a tremendous amount to adjust for multiple testing error. And these adjustments are pretty much never done. So the adjustments that they do use are not aggressive enough to to eliminate multiple testing error. P-hacking, let's see, this is another example of p-value error. This I actually saw recently in a COVID study, but this example I'm showing you is an older one. It showed the effectiveness of a drug after 8 days, after 30 days, and after 90 days. So what's wrong with this picture? What's missing? Well, 30 days, they had significant increase. 8 days, they had significant increase. 90 days, they had a significant increase. What it didn't show you was 60 days. At 60 days, they did not have a significant increase. So if you leave it out, you see a nice curve. But in modeling, we say that if you put in the 60 and the 60 is way down here, in modeling, we say that, hey, your model doesn't rank. You have a pattern of increasing, of improved outcomes with increasing treatment length, but not for the 60-day level. They threw it out. So that's picking and choosing based on p-values, p-hacking. Okay, this is going on to philosophical territory. A lot of the problems you run into in measurement and clinical practice improvement are due to big dog decisioning or monopoly power in general. That causes entry. Monopolies are associated with higher costs, with high quality, but lower quantity than socially optimal. So that pretty accurately describes our healthcare system right now. We have really, really good healthcare if you get to see a doctor, but overall not enough healthcare at too high a cost. And that also applies to the medical technology relationship too. But I won't get into that too much here. Because what I want to get to is follow up on what I said I would say a little bit more about, which is going back to two of the products, scorecards and campaign evaluations, and just share a few tips, my personal ideas of what makes them effective. In terms of benchmarks, whether you're using them in an evaluation tracking report or a dashboard, they need to involve providers from the start. And that's what I mean by collaborative. But watch out for death by committee. If you just say to a large group of people, well, what do you think? You'll end up with the lowest common denominator thing that doesn't work or becomes way too complex. At least that's my experience. So how do I deal with that? Sometimes it's good to decide in a small group with the right people in the room. You do need representation from all the important stakeholders and all the subject matter experts. But you don't, I mean, representation from each of the subject matter areas, but you don't need every subject matter expert in there. A small group, and then you find the right influencers, and then you steer the larger group toward that. That's one way to deal with that. And at every stage, keep analysts at the table so you have that continuous dialogue between the data and the people who are going to be solving problems. Okay. They have to be relevant. Benchmarks are sometimes based on inertia and old assumptions. Find the experts and ask if achieving a certain benchmark will drive the triple aim. Is this really going to matter? Consider patients as well as non-patients. I'm just thinking about the class composition here. If you're just in a point of care healthcare providing setting, that may not be as much of an issue. But if you're thinking about healthcare systems and healthcare policy, patients people spend at best less than one. It's a there's like 5/100 or something, a percent of their hours in a year in a doctor's office, and many patients don't get into a doctor's office. So consider the non-patients also, population health, and setting benchmarks. The benchmarks need to be clear, that is easy to understand, and easy to replicate and confirm, so other people can follow along and they can manage to those metrics. They need to be easy to relate to behavioral change. So when the doctor or some other provider or practice sees the metric, they can say, okay, here's what I need to do to improve the score. The metrics need to be timely. That is, they need to be available with sufficient frequency and with low enough latency to allow providers to course correct. If you get information 6 months after a period of behavior, it's a little bit too late to do anything about it, especially if, let's say, you're doing a quality improvement program, and since your program, you're going to pay people, and you're going to be paid in 3 months, but you don't have enough time to change based on the interim report you got, because the interim report you got was just 3 months before the end of the program. 9 months already done. You can't influence the average performance metrics very much, so it needs to be timely. They need to be achievable. So it's like a carrot in front of a donkey. If it's too close, the donkey just bites it and that's it. No incentive. If it's too far, it says forget it. It just ignores it. So you need one area where you get unachievable targets is when the target is a single number. So if you have a fixed target, like CMS often uses something like 80%, 80th percentile nationally as a target. Well, if you're way, way, way below it, you're at 20, it's like, there's no way I'm going to hit it. So there's no motivation there. There's no incentive there. And if you're too close, then it might not motivate change, which might be okay if it's good enough. But you also have to worry about risk. So I have an example, an actual example, where a Texas program, healthcare program, they had, well, this is something I like, which is gap closure. You get paid if you close the remaining gap by a certain percent. But the way they defined it, just 10 patients more or less, 10 patients fewer or more, and we're talking about 50,000 patient population. So just natural variation, or if there's just a rainstorm or something, to make a $1 million difference. That's too much risk. That's not reasonable. You can't run a business that way. They must be fair. So that means that the metrics need to be either normalized very heavily or rigorously peer grouped, tiered. And also for fairness, you'll want to allow for diminishing returns. The fact that if you're starting from a very low level, it's much easier to get, let's say, a 5 percentage point increase than if you're starting at a very high level. Even if the target is a percentage increase, let's say I want you to increase your annual wellness visit rates by 10%. Still, if you're starting at a very, very low level, you have low hanging fruit you can convert. But if you're starting at a high level, even to get a 10% increase, even though 10% increase is a smaller number, empirically, very often that is very hard to move because all the low hanging fruit has been picked, and the people who aren't coming in for annual wellness visits are have a good reason. They are resistors, hard targets. I did mention that, however, that one way to deal with that is to have, because the difficulty of achieving an increase is often nonlinear, I do like gap closure. Gap closure means instead of increasing by a certain percent or trying to reach a certain number or increase by a certain number, gap closure means you pick a target The target needs to be fairly chosen through a collaborative process, et cetera, et cetera. You take a target, take where you are, and your target is to close X% of that gap. So if you're very far from that target, your gap closure target might be 20% of the gap. But that 20% is a big increase. And if you're very close to the target, 20% of the gap is a very small increase, and that's fair. Because, like I said, if you're starting very high, it's much harder to make small gains. You do want to watch out for buckets and tiers. That's another way to deal with nonlinearity. You could say your first target is 50%, your second target is 80%, your third target is 85%, right? To get your next $1 million, let's say you only have to go from 80 to 85%. You have to worry about those targets because you also have to allow for random variation and fuzziness of data. So this was a real example. The target was 80%. But if you were at 80% already and you drop down to 79.9%, you would lose $5 million. Again, that doesn't work for a business. You can't run a business that way. And it has to be efficient, it has to be administratively light to track and to use the program. And so one example where it wasn't efficient was there was a really detailed incentive program that paid out checks as small as a few dollars and some under $1. It costs more to open the envelope than to cash the check, right? It has to be simple in terms of a parsimonious set of metrics. You know, the scorecard I showed you had 2 metrics on it. We went through a lot of work, primarily with doctors, to agree on 2 metrics, because the complexity not only muddies the message, but it also increases the workflow for the practitioner in order to participate in the program. And after launch, it's very important to use contact strategy, such as a CRM, to keep the goals and the progress top of mind. And that leads us to the end. So I think actually we do have, there's a question mark here, there's another, not a check, but this is also the end of this lecture. Thank you.